Thank you for the introduction, and thank you very much for the organizers for the opportunity to participate at this conference and to the opportunity to do this talk. And I want to tell you something about obstacle problems with an additional condition. So first of all, the general form of an obstacle problem, we take a nice operator script A, mapping from a Banach space into its dual. And we want that A of u is greater or equal some f. We have an obstacle psi, so u should be also greater or equal than psi. And both conditions are coupled via this equality here. So A of u minus f applied to u minus psi in the right reality should be 0. And this means this is also somehow a minimality condition, because if A of u equal to f is on the part of the domain where A of u is equal to f, since this member will be 0, u is allowed to be greater than psi. And we have also the free set, there u is equal to psi, so this member will be 0, and therefore A of u is able to be a little bit bigger than f. Okay? And we can do this obstacle problems for elliptical PDE. Then the script A of u will be some A of u, where A is some as operator. The same we can also do for parabolic PDE. Then script A of u will be time derivative of u plus A of u from the elliptic case. And finally, we can also do this for stochastic PDE. And then script A of u will be the time derivative of u minus some stochastic integral plus A of u from u. And what I want to add is the so-called Lewy-Stampaccia's inequality. So we have been talking about some inequality from below. And Lewy-Stampaccia is now something which gives us a bound from above. And the bound is given by this f and the obstacle and the negative part. Okay, and here negative part. And so when you want the take-home message of this talk will be the Lewy-Stampaccia inequality. So let me mention some applications where obstacle problems may appear. So we have some Signorini type problems where we apply a force to a membrane. And if there is no plate, so the membrane is somehow in the space, and if we have no plate, then we have no obstacle. And if we have a plate, so the interface between the membrane, so the plate is the obstacle and the membrane touches the plate. And we have also this phenomenon, if we look at Stefan type problems. So this is when ice is melting into water and with the temperature. So here we have the free set where u is still ice, so u is equal to 0, and outside we have the heat equation, and u is greater than 0, and this is the small version of it, and it can also have the big version here. Okay, and we have also this obstacle problems in fluid flow in porous medium. We can find constraints on the pressure or also for vehicular traffic jams. So obstacle problems appear very often in applications. And I want to present to you a work about a stochastic pseudomonotone parabolic obstacle problem. So for t greater than 0, we are on a bounded Lipschitz domain. We have a stochastic basis with the usual assumptions. And we study existence and uniqueness of the following variational inequality. So we have reformulated the variational inequality using some rho, which is often also called a Lagrange multiplier. So our solution will consist of u and rho. And okay, we want that u and rho solves this SPDE here with an initial value u0, which may also be random and has to be greater or equal than the obstacle evaluated at 0. We have homogeneous boundary conditions for u, And here you see the obstacle, so u is greater or equal than our obstacle psi. And okay, and this minimality conditions you saw on the first slide is ensured by this condition that rho applied to u minus psi should be 0. And okay, the pseudomonotonicity comes from this operator. So this operator minus divergence A is a pseudomonotone so-called Leray-Lions operator, which maps from the Sobolev space W1P 0 to its dual space. And here the value of P may be less than 2, but still big enough that W1P is embedded into L2. Okay, F, this number here, is predictable and with values in W minus 1P prime, and psi is an appropriate random obstacle function. So let me first talk about this pseudomonotone operator. And usually such an operator is induced by a Kara-Theodori function A. And for this Kara-Theodori function A, we impose a monotonicity condition. It is this one. And then we have also some coercivity condition, which you can find here, which is formulated, of course, in the growth is here in P, and some Q, which is depending on P, which gives us, well, which provides that the solution will be in the right functional space. And then, okay, we have also a growth condition here, which provides also some bounds on the solutions, and of course depends here on P, as you may see. And then we have also some with respect to the second variable. So here, please note that the monotonicity is with respect to the last variable, and the second variable is the same in both expressions. And here, with respect to the second variable, we assume some Lipschitz condition, some generalized Lipschitz condition. And well, what I have in mind when I think about such an operator is a generalization of, well, my favorite operator, which looks like this. So we have the minus divergence of gradient of u to the p minus 1 gradient of u plus some f of u, where f is some Lipschitz continuous flux function. And please note that here the divergence includes also the f of u. And so the first guy you see here in blue, this is called the p-Laplace operator, which is a nonlinear operator defined on the Sobolev space W1P0. And you all know the special case if p is equal to 2. So this member here vanishes and you get just a Laplace operator. And why should one consider such a strange operator? Well, there is some contribution of Diaz and Dételin, where they study flow through porous media in a turbulent regime. And there they propose a nonlinear p-power type version of the Darcy law, where the p-Laplace operator comes into play. Then physical quantities may be transferred due to diffusion and also convection. And that's why one may add this first order perturbation minus divergence f of q to address convection effects. And finally, of course, we will introduce randomness on the right-hand side of the equations. And you can think about this as a random external force, well, which covers all uncertainties and multi-scale interactions, which may appear in the model. So, before I start with introducing our results, I will give you some previous results, and the list is far from being complete. So first, I think the work started with elliptic equation in the deterministic setting by a sequence of papers by Mokran and Murat. Then there has been some works by Mokran and Vallée, and Mokran, Vallée, and Hawi, which includes some variable exponent LP spaces, so variable exponent functional setting. Then we had some contributions to parabolic pseudomonotone equations in the deterministic setting by Donati, then Guibet, Beaugrand, Tahraoui, and Vallée. And Guibet, Tahraoui, Vallée, where here you have L1 data and a renormalized formulation within the Lewy-Stampaccia inequality. And finally, there is, then we have one previous contribution in the stochastic setting, which is parabolic, but the operator considered by Tahraoui and Vallée was t-monotone, so the analysis was way more easy than the case we want to consider. And finally, a recent contribution by Biswas, Tahraoui, and Vallée, where they consider conservation laws in the stochastic setting. And so, in the joint work with Niklas Sapon-Soubleau and Yassine Tahraoui and Guy Vallée, which I want to present here, our aim was to address Lewy-Stampaccia inequality for a pseudomonotone parabolic equation with both additive and multiplicative modes. So it's somehow the generalization of this. So I will quickly define what my Wiener process is. I have a sequence of independent FT Brownian motions. I fix a separable Hilbert space such that L2 is included, and then I fix a non-negative symmetric trace class operator Q such that Q P1/2 is L2. And then I can construct my cylindrical Wiener process by taking an orthonormal basis made of eigenvectors of this Q with corresponding eigenvalues, and then, we all know that this will be an FT-adapted Q-Wiener process with values in U. And then, if I have a predictable square Wiener process with values, so these are the Hilbert-Schmidt operators from L2 to L2, then the stochastic integral in the sense of Ito may be written in this way, where here we have the integrals with respect to the Brownian motions. So this is the Q-Wiener process I want to consider ascribing this. And now what noise I want to consider precisely. So again, Hs of L2 is always the space of Hilbert-Schmidt operators from L2 to L2. And my noise will be denoted by G. It's mapping from, so here omega t is omega times 0t, so it may depend on omega, small t, and u, and maps into the Hilbert-Schmidt operators, and it's given by a sum of something which is additive and multiplicative part, and of course G and sigma are predictable. G has values in the Hilbert-Schmidt operators and sigma as well. And here for sigma, we also assume that it is 0 and 0, and we assume that it satisfies a Lipschitz condition with some nice Lipschitz constant L. So this is the noise I want to consider in the stochastic. So the stochastic integral I want to consider. And let's now go to the assumptions on the obstacle. And so the most important thing is, so for the obstacle, is the order dual assumption. And as you may see here, so psi is my obstacle, which is basically a function which is LP with values in W1P intersected with L2, and predictable. But when you go to the order dual assumption, you see here the time derivative of psi minus the stochastic integral going up. And so if we want to give a sense to this one, we have to assume that this time derivative has a nice regularity, and the appropriate regularity is LP prime with values in W minus 1P prime. And okay, this is my equation, and the equation is coupled to the obstacle by this ordered dual assumption. So please note that we have here the f, and the f is popping up here as well. So this is somehow the coupling. And the most important thing for the ordered dual assumption is that there exists some non-negative elements h plus and h minus of Lp prime omega times t with values in w minus 1 p prime, such that this expression f minus the time derivative of minus stochastic integral plus the divergence of the obstacle is equal to h plus and h minus. And please note that since we have a dual space here, the non-negativity is interpreted in the distributional sense. Okay, so of course this is not a non-negative function, but when you test it with non-negative test function, you get something non-negative. And again, another take-home message is maybe why are we considering the ordered dual assumptions? It's very, very important because it provides additional regularity on this Lagrange multiplier rho, which is here, and it provides well-posedness for Lewy-Stampaccia's inequality. So we cannot prove Lewy-Stampaccia's inequality without the ordered dual assumptions, and the ordered dual assumption provides that this member rho will stay in a reasonable space and will be not, for instance, some measure. Okay, and if you see, you're not allowed to plug in 0. Psi equal to 0 is not allowed, because if you would plug in psi equal to 0, please recall that G was the sum of some additive noise plus some multiplicative, which is 0 and 0. So the multiplicative member would disappear. So we will end up with a stochastic integral over some function G here, and we would have a time derivative, and this is not in this space. Okay, so we are not allowed to, unfortunately, we are not allowed to take 0. Okay, so what is Lewy-Stampaccia's inequality? We have a solution to our variational inequality, and we want that this Lagrange multiplier rho satisfies some inequality. So this is naturally given, so that minus rho is greater or equal than 0 is naturally given by the variational inequality, but we want to have also that minus rho is less or equal than h minus, which is provided by the ordered dual assumption. So h minus, you have seen it in the previous slide. It's just this expression. Okay, so let me give you the notion of solution I'm working with. Since my operators are nonlinear, I take the variational formulation of the solution. So U has continuous paths with values in L2. We have a spatial regularity of U in W1P0. We have, of course, the initial condition, which satisfies the obstacle U is greater or equal than my obstacle. And here the Lagrange multiplier is in Lp prime with spatial values in W minus 1P prime. Its minus rho is greater or equal than 0, of course, again, in the distributional sense. And here you see the minimality condition, so expectation of the integral of the duality of rho applied to U minus psi, it should be 0. And this equation here should be satisfied for all t, p almost surely in omega. And these integrals here, of course, have a meaning as Bochner integrals. Okay, and the main result we were able to achieve is that there exists a unique solutions to our variational inequality, and moreover, this solution satisfies Lewy-Stampaccia's inequality. So, small theorem. And okay, the rest of the talk, I would like to give you some ideas how the proof can be done. And first of all, this is pretty standard in this variational inequality techniques. You switch the integrand in the stochastic integral and the operator by plugging in the maximum here. Usually it would be u epsilon. Now you go to tilde and you plug in the maximum between psi and u epsilon. And the same you do with the operator. It does not change the properties of the operator, so it's perfectly fine for the theory. So this is one thing you do, and the second thing you do is you add a so-called penalization term here, which is 1 over epsilon, so it's singular as you see, u epsilon minus psi, negative part with a minus, so it's negative. And okay, these are the modifications you do for the equation to study the variational inequality. And okay, you will hope that this guy will converge to rho as epsilon goes to 0. But first problem is that existence and uniqueness of this approximated problem have to be provided. So we did not find this result in the literature, so we had to provide it. And for this, we use the standard theory of locally monotone operators. You can find it, for instance, in the book of Leray-Lions. And to apply this theory, we used the higher order perturbations. So we added we had an additional parameter delta in the equation. And here an operator G of u epsilon, which is somehow a higher order perturbation. So here you have a parameter nu, which is very high, and another parameter m, such that all the injections are nice. And so we have a nice leading monotone operator here. And in this setting, we can apply the conditions of Leray-Lions. And then we can conclude that for any delta, we get a solution. And okay, then we have to find compactness with respect to the parameter delta. So we fix epsilon. And we look at the sequence of the laws where we put in our approximate solution u epsilon delta. We put in the stochastic integrand with the tilde, so the modified one. We put in the obstacle psi and also the two ingredients of G, namely little g, which is additive, and sigma, which is multiplicative, and of course the noise and f and u naught. And we can find tightness and appropriate spaces for this law. And then we use Prokhorov's theorem and a generalization of Skorokhud's theorem, which has been introduced in the appendix of Gyöngy-Krylov and Finan-Dimby. And we get the existence of some new random variables, u epsilon delta bar, g u epsilon delta, g bar of u epsilon delta bar, psi bar, little g bar, sigma bar, w bar, f bar, u0 bar, and u epsilon infinity bar, of course on a new probability space. And thanks to so they coincide in law. So these guys, except for the epsilon infinity, coincide in law with the previous objects. And so we can see that the g bar of the u epsilon delta bar is in fact little g bar here plus sigma bar of the maximum here. So it's well known. It's standard procedure. You recover the structure of your object, and you recover also the equation on the new probability space, and you gain convergence. P almost surely for delta going to 0, which you did not have in the original space because you just had some weak convergence. Okay, then we can pass to the limit on the new probability space. Therefore, we use our a priori estimates so that we have identity in law, Vitali's theorem, and the reconvergence results. And at the limit, we find this equation here. And as you may see, we have here an A infinity, which is not our, which we have to identify to be our Leray-Lions operator. And this is possible if we use an energy inequality with respect to a weighted exponential norm. So this is classical. And then we combine it with a stochastic version of Newton's trick as it was adapted by from the book of Dirichlet. Okay, and this pseudomonotonicity argument, I would like to say, gives us the right to say, okay, A infinity is this expression. So here we can plug in the right thing. Then next we want to go from the new probability space to the old one. And therefore we use an L1 contraction principle to show pathwise uniqueness of solutions. And then we use the result of Gyöngy-Krylov from '96, which tells us that in this way we get the convergence in probability up to a subsequence on the of our approximate solution on the original probability space. So, okay, we can remove the bar in the equation. And, okay, this is what we end up as approximate equation. And as you see, what is still left is the A tilde, so the maximum, and the parameter epsilon we have to take care of. So let's go to the limit with epsilon to 0. And the good news is that since this guy is monotone, we have almost surely convergence of approximate solutions. So we don't need to use some martingale solution argument at this step. Bad news is to provide regularity of this term, we need to add some regularity to our ordered dual assumption. So before I told you that H minus was LP prime with values in W minus 1P prime. And we have to now to improve this and say that it is in L alpha with values in L alpha, and alpha is the maximum of 2 and P prime. And this is a result that we allow P to be slightly lower than 2. So we have to work with alpha here. Okay, so now the new order dual assumption looks like the old one, but with a more regular H minus. And okay, as I told you, since this guy here is monotone, we obtain that the sequence U epsilon is non-decreasing as epsilon goes to 0. Then, thanks to the regularity of H minus here, this is really the crucial point where the additional regularity comes into play. We may bound the singular term in L alpha, with values in L alpha. So you see it really here. You get so the fact is that this singular term inherits the regularity from the ordered dual assumption. So this is somehow the crucial point. And that's why we are able to bound it in L alpha. And, well, it is not so difficult to show that U epsilon minus psi minus, so the negative part of this guy goes to 0 strongly in L2. And therefore, now, since this sequence is non-decreasing in epsilon, we can define U to be the supremum of all this. And with the good a priori estimates, we know that it is a nice function. And since we have boundedness of the singular term in L alpha, we have at least a weak limit rho in L alpha with values in L alpha here. And in addition, since you see that U epsilon minus psi minus goes to 0, so the negative part of this goes to 0, and as a consequence of course, u minus psi, u will be greater or equal than psi, okay? Because we just showed that the negative part is 0 with the, since we have here the right convergence to u. And minus rho is greater or equal than 0. We get this because, as I told you, this guy is negative. So if we multiply it against a non-negative test function, it will stay negative. We can pass to the limit weakly because we have this result, and this is how we obtain the distributional formulation of this result. And finally, we get this result by plugging in for rho this expression, and for u minus psi, u epsilon minus psi. And we have enough convergence. We have here weak convergence. We have strong convergence. We may pass to the limit. And we can realize that since we have here a negative part, we will also have just a negative part in this guy. This will be 0, and we will this will go to 0, and then we obtain this result. So finally, when we plug in everything into the equation, we end up with this expression here. And please note, I did not mention it as point on the slide, but of course, before, here we had u epsilon and the gradient of the u epsilon, and since this is a pseudomonotone operator, we have to repeat the procedure of Minty's argument to say that the limit is really equal to the divergence of a tilde of u gradient u. Okay, once we have this, we can remove the tilde, because as maybe, let me recall that a tilde was done because we have taken here the maximum, a tilde of u is here the maximum of u and psi, and the same here. You have in g tilde is g of the maximum of u and psi. So as soon as we have this result, we can remove the tilde because the maximum is, in this case, g is equal to g tilde and a is equal to a tilde. So we end up with this equation, which is nice, but still we want to drop regularity from the dual order dual assumption. So the bad news is, first of all, we have to add regularity. We have to add some regularity to the order dual assumption and say something about the regularity of the time derivative, because we still have to show that our solution satisfies Lewy-Stampaccia inequality. So we want to prove this. And to prove this, we go on the level of approximations. And we take our singular perturbation and we add and subtract h minus. Then we realize that plugging in one h minus into the parenthesis makes it smaller, so we end up with this term. And this is the reason why we need this regularity here, because now we have to write the SPDE for this expression. So here we have the h minus. We used an equal formula for a smooth approximation of the negative part to the square to obtain an SPDE for the norm of the negative part of this guy, so the A2 norm of this one. And for epsilon to 0, then we can show that this expression goes to 0 strongly in L2. And this is in fact a very technical part. So this is really, we have to use some point-wise, almost sure arguments, and really be careful with our pseudomonotone operator. So this is the technical part of this proof. But once we have this, we can use for any epsilon an arbitrary test function phi. We multiply our singular perturbation by phi and integrate, and the same here. And then we can pass to the limit with epsilon. On the left-hand side, we will obtain rho as a limit of the singular perturbation, And on the left-hand side, since this guy goes to 0, we end up with minus h minus phi. And this is exactly if you multiply minus on the other side. So this is the variational formulation of this inequality. Okay, so we have completed our task. And now the last part is to pass from a very regular ordered dual assumption to our ordered dual assumption with values just in the dual space W minus 1p prime. So this one, and this we do basically by approximation. So we approximate our h minus by regular ones. Then we may define the fn's associated with the hns. So this is, well, no problem. And we find that fn converges to f and lp prime w minus 1p prime. So we have convergence of this thanks to this convergence. And okay, with our previous results, we have the unique solution with respect to the regularized problem, and we have all the we have also Lewy-Stampaccia and the variational inequality. And okay, the Lewy-Stampaccia inequality at the limit now is obtained for free just by weak convergence. And okay, for the passage to the limit in the equation, we have again to put on the machinery with martingale solution, Prokhorov and Skorokhod. But since pathwise uniqueness is available at the limit, this can be done. So this is what I wanted to tell you. I thank you for your attention, and I'm looking forward for questions.